And thanks everybody for joining. Today we're going to be talking a little bit about carbon fiber and actually not just carbon fiber, but did you know that we also offer other fibers, Kevlar, fiberglass, and then a high temperature variant of fiberglass. I think we've gotten a lot of questions over, at least over my last 3 or 4 years here at the company on which fiber should I use, how much fiber should I use, and I think it is. We always kind of have to go examine the case and talk about it. And I think internally, like you've got your own workflow for it. I've got my own workflow for it. And today we'll talk about some of our best practices and some of the information that goes to inform our decisions when we decide which fiber should we use and how much we should use. So hopefully that is pertinent to everybody who's on this call today. So for just a brief introduction here, I'm Charles Liu. My hair is a little different. I think I actually shaved my head in that picture. And I have been an application engineer at Markforged for the better part of the last 4 years. Now I'm actually in product marketing, but I still like the application engineer title because that's mostly what I do.
And I'm Oscar Molina. I have been at Markforged for a little bit under a year as an associate application engineer. Like Charles, my hair is also slightly different from that picture. Part of how the pandemic has changed people's hair. It's definitely represented here.
Cool. Let's see. So today's agenda, what are we talking about today?
Today, we want to run you through the basics of Onyx versus CFR and kind of dig into that for those of you that are maybe not as familiar with it. Then we'll step into some customer stories to see some of the use cases where customers have leveraged fiber and sort of what fiber choices they have made and what they have decided to do with the fiber. And then we'll step into sort of workflow and principles for fiber applications. As Charles mentioned, we all have our different workflows, but there's some key ingredients in there that are needed for proceeding with using fiber and addressing those questions at the beginning. What fiber, how to route it, do we even use fiber to begin with? And then at the end, we'd love to open up to questions, and we'll be doing questions throughout the entire webinar. So make sure to put those in the chat and we'll try to take some pauses throughout the presentation to discuss with you. And right now, yeah, a good question before we dig into it. One question came through about workflow. So what we mean by workflow here is sort of the process by which you address whether you need fiber. So, you're going to start off with a part that you have in mind. And, question number one is, what are its functional requirements? And then the steps that precede afterwards for figuring out whether you need to put fiber into it, what type of fiber you're going to select. So that's sort of what we're referring to when we say workflow here.
Yeah, it's a thought process.
A thought process, a methodology for design and the use of fiber.
Cool. So first, we want to ask a few questions. I think we've got some polling set up. So I'll allow about 30 seconds for the poll. So get your answers in quick. The first question is, have you completed Markforged University? Now, this is not a plug for Markforged University. I shamefully, personally, have not taken it because it was built while I was here. And I guess I contributed to some extent to it. And the person who built it, Nick Sunday, is a good friend. So I figured I don't need to listen to the guy talk for that long. But the pieces that I've seen have been super helpful, and he spent a lot of time on the graphics and making sure that the content was visually useful. I definitely recommend it, at least based on what I've seen.
Yeah,
Oscar, you've taken it.
I've taken it, which was sort of how I was onboarded when I joined Markforged, and so it took me from 0 to 100 very quickly as far as understanding fiber reinforcement and understanding 3D printing, especially with relevance to the Markforged platform.
Sweet. So just end the poll now. And it looks like we've actually got a pretty high number here of people who've taken it. So I'm just going to put that out there. Thanks everyone who has taken it. And for those of you who haven't, again, this isn't a plug that you have to take it. I think it is useful if depending on what you're trying to learn. And if any of the stuff today resonates with you, then maybe we can get in touch with us and we can figure out how we can get some more of that content out to you. What is relevant, what isn't relevant. Cool. Well, I guess we can do that second poll question later. Sweet. So let's go this is actually a slide that I pulled from a previous webinar that I did about carbon fiber, and specifically about carbon fiber. But obviously there are a number of different fibers. What I want to talk about is some of the basics behind the differences between the two materials. I would say based on a lot of what we've seen, the majority of customers are going to use onyx, right? And the majority of the material used is onyx. There's a good reason for that, right? So the chopped fiber in onyx actually adds a lot of material properties to the that you might not really expect. So some of them include better printing, and you see that, right? You see that, and you think, well, isn't Markforged just like it's the printer, it's the software, but it's a combination of all the things. It's the hardware, the software, and the materials. And one of the kind of sneaky cool things that we did with onyx is we added a range of fibers in there, and it's different from the typical range of fibers that you would see from another FFF like carbon fiber based material, because a lot of people are going for strength, right? And we've got the strength through continuous fiber reinforcement inside the part, so we don't need to add longer strands of fiber into the onyx in order to get the strength. That ends up actually kind of ruining the surface finish in a lot of cases, makes it hard to print. So we blended onyx with the idea of optimizing print quality, and that's kind of what you're seeing, like print quality and accuracy. The CFR, the continuous fiber reinforcement, as you know it, that's the continuous toes that go into the part that essentially can, I guess I would say 10 to, well, with fiberglass you get probably 5 times the strength of onyx, right? And then carbon fiber is like 20, 15. So it's a pretty significant difference between onyx and like continuous fibers, and it reminds me a little bit of the difference between essentially two different types of cars, right? You've got like your kind of runabout sports utility vehicle that will really do a lot for you, right? It'll take you up and down the slope to a ski slope. It'll take you out camping. It'll haul some of your small toys. It might even haul like a pretty decently sized trailer. I think these Subarus can haul like, I don't know, 2,000 pounds or something, 2,500 pounds. But the continuous fiber reinforcement is sort of a next level thing. And I'd say a lot of you here probably know that. So that's kind of goes without saying, but it's going to allow you to go a lot further with your application, take 3D printing to places that it didn't go before, but it also functions as a daily driver. So it's just a matter of like balancing the cost and the practicality of using which material. So that hopefully we'll talk a little bit more about that today. So a little bit on short fiber filled filaments, just to kind of give a quick summary. The fibers that we're using are in the order of 5 to 10 microns in diameter and 50 to 250 microns in length. So aspect ratio wise, they're quite long, but just relatively long to their thickness, but they fit into the material and they stabilize the material as it's being printed. It also adds a good amount of stiffness because the fibers are aligned with the print direction, and essentially anytime you load the part, it is taking up that slack and then putting it into like kind of deflecting across different beams, like a stack of spaghetti in some ways. And so the majority of the things that you get from this, the benefits are you get the increase in strength and stiffness. So that relative to base nylon is pretty good. You also get improved thermal stability, which just for us, that's 2 things. One, in application, it's going to be, it won't heat as much locally. It is like marginally more conductive. And because it's in a small amount, that improves print, like the actual printing process. By putting the carbon fiber into the material, it's allowing the heat to dissipate like on a kind of micro scale, which allows it to print better. And then it also gives you just better part accuracy because it's not like deforming as much and warping during printing. You're just going to get better accuracy. So some of the challenges for this, it's abrasive to print. You've run through probably a number of nozzles at this point, and those are hardened steel, right? So if you imagine putting put this through like a brass nozzle,
it would just wear it completely. And fun fact, we did try a variety of materials on the nozzle, so we're familiar with what printing these materials can do to it. But with the current nozzle state, you are able to get a longer lifetime out of it than possibly using some of those other prototype nozzles we had at one point.
Yeah. Yeah. And so like I was saying earlier, the longer fibers, we can use a blend or a different range of material, like fiber lengths, but ultimately longer fibers or too much fiber can negatively impact surface finish and part accuracy. So we've blended this to be kind of optimal for printing. Now, when we were talking about like relative strength comparisons, I just wanted to give you a base order of magnitude. So you've all got access to the data sheet, and it's when you look at the number for continuous fiber, you're like, wow, that's like 450 megapascals for flexural strength, like, or 540, must be a little dyslexic. Right? That's really high relative to the 71 megapascals for Onyx. And that's like in an ideal scenario, right? Where you're using this 100% in a flexural beam. So when we do that test, it's really in a practical implementation, you want to figure out what volume of what volume fraction of the continuous fiber reinforcement you're using relative to the rest of the part. And that's something that we can kind of work through. But for just like for comparison purposes, it really is about an order of magnitude difference in strength. So by adding even 10%, you could be doubling the part strength, and 20% could be tripling it. So there's I think a little goes a long way with the carbon fiber, especially when I'm going to drop a little sneak preview of what Oscar's going to talk about, which is a little bit about beam bending theory.
Correct. So we'll dig into sort of how that works. And we did have a question come in as far as why our Onyx material is superior to other 3D printer OEMs, similar material of this nature. And so I would say comes in sort of multiple aspects. One of those being, as Charles mentioned, sort of the strength properties, but beyond that, we're not simply chasing just strength properties. We're chasing surface finish. On our industrial series, you're able to print 50 microns, with the highest grade quality, where you get, as we like to say, an injection molded type finish on the surface. You also get the repeatability because we've designed our own material and tuned our printers to it. You have that coming in. So it's both, a aesthetic type component to why our Onyx material is superior, as well as it not compromising any of that strength that comes inherent with having chopped carbon fiber within the nylon.
I think this slide is just a quick illustration of what internally you're looking at with the continuous fiber reinforcement. So this is a cross section of a fiber part, right? And here's each of those little pins is a fiber. And the way that we're printing this, these aren't actually the fiber filament that we print. Like the fiber filament that we print is actually a bundle of fibers. So as we're ironing those down onto the part with that fiber nozzle, these are it's turning that bundle into a flat kind of rectangular cross section material, and then it's ironing those all together. So it bonds them all together. So visually, that's kind of what you're looking at. The question related to comparing to other OEMs or other fiber-filled nylons, well, we actually see them claim a range of numbers, and sometimes they'll claim like up to 120 megapascals, like 110 megapascals, but they're using a dried injection molded sample. And we're actually going to probably release a research paper soon. I saw that this morning, this fresh, hot off the press. We did an investigation of our materials, our own materials, dry injection molded samples, conditioned samples. Really the standard that you should work to is a conditioned sample, because practically speaking, one, you're not injection molding nylon.
No.
So that's like a major difference. And then two, atmospheric conditioning is a real thing that happens to a number of thermoplastics. And you want to condition your part in a way that it's absorbed some amount of atmospheric moisture so that it's like accurate representation of what you're doing. A lot of the competitors that we've used will just kind of cite their suppliers' data, which is using a dried injection molded sample. I think that's fine if you're in the plastic injection molding industry, but that isn't really accurate for 3D printing. So based on what we've seen, somebody who might claim 110 megapascals really is getting 60 at a conditioned state. And you can kind of see this comparison here going between Onyx. Like, as I said earlier, Onyx isn't tuned for like strength really, right? We're saying that Onyx is built for surface finish and accuracy because we can get strength from other ways. And you can see on the right side of the chart here, as you add continuous fiber reinforcement, it is pretty dramatically changing the strength of the part. So by adding just 20% fiber reinforcement, so on a 10 millimeter section, having one pass, one concentric ring on a 10 millimeter section gives you 192 megapascals of tensile strength.
Yeah.
And that only goes up. So I'd say in comparison to other fiber filled materials and like other OEMs who make those materials, we're giving you a range of like, so on the low end, I'd say like our material is tougher than a lot of other similar nylons because we haven't filled it with so much fiber.
Mm-mm.
And then on the high end, by adding continuous reinforcement, you're getting the ability to add strength to get close to aluminum, really.
Correct. Yeah. Sort of a Baskin Robbins type of situation. You figure out what toppings you want in there. And so you're able to go from base vanilla flavor, if you will, all the way up to like 20 toppings within your ice cream. And that's when you're packing your part full of fiber. And on top of that, which fiber you want, whether that's Kevlar or carbon or a fiberglass.
Yeah. Sweet. And as far as the relative comparison goes, this is a fun Mountains of the Solar System map that I saw at some point in time, and I thought, well, like this is pretty relevant. I think we down here on Earth will think that Mount Everest really is just this daunting mountain that like really like I don't plan to go hike Everest. If some of you do, it's like more power to you, and I wish you good luck and good fortune. But when we're comparing the types of materials out there, like the continuous fiber reinforcement is kind of otherworldly in that it allows you to take what is essentially what you already think of as a quite good material and elevates it to a different level. So I thought this is a fun chart for comparison. Ultimately, what that allows you to do is it moves you beyond like concept model and prototyping, right? And I think even still with Onyx, you can still do some amount of functional testing and validation, but as soon as you get a little higher up, the number of I'm not saying that you can't do work holding and alignment tools in just Onyx, right?
Mm-hmm.
I would say it's just the percentage that you can do is reduced a bit. In some cases, a lot of these tools that you print in Onyx will work just fine, right? If they're under compression, they're not under some like really strong flexural load, maybe they're only used periodically. There are a lot of use cases for just Onyx in these applications, and like very obviously a lot of you have found them. But when you're able to add that next order of magnitude of strength with the fiber reinforcement, I think you can expand the number of potential applications that you have. So that's just sort of what we're saying about our sweet spot as far as application space goes. So yeah, how are we doing on questions?
We got a couple of questions coming through, a couple along the lines of chemical resistance with Onyx and carbon fiber parts. Any experience there, Charles, of what you've heard on chemical resistance with our Onyx material?
Sure. Ryan, Onyx is based on a nylon 6 blend. Or nylon 6/6 blend.
Yeah.
It's a nylon 6/6 blend. So if you wanted to just look up like general nylon chemical resistance properties, we're pretty similar to those. We have a chemical resistivity slick that we can send over if that's something that would be useful to you. I think it's actually might be available on the website if I'm not mistaken.
Yeah.
So we personally, I don't think we've done too much as far as testing goes. I will tell you that the nylon family of materials, so the polyamides, are susceptible to strong acids and bases. So you don't want to submerge in acids and bases, but any sort of like a solvent, other types of solvents, fluids, like even acetone is not going to really do a whole lot to it. We talk about like vapor polishing of ABS parts of that, right? Vapor polishing of ABS or PLA, that very unfortunately doesn't work for us.
Yeah.
I'd love to polish some parts to a mirror finish, but
Mhm.
we're just not going to be able to get that.
Yeah, we have done some vapor polishing that's gotten kind of close to it where, you are able to get rid of some of those layer lines, but it is a matter of experimentation and finding someone that can help out with that and testing out different suppliers for vapor polishing techniques.
Yeah, there was a very specifically one that I think I published recently about AMT. I also try not to make a sponsorship plug here, but there are different types of post-processing companies that I'd say largely work with the multi-jet space. So they work within like the binder jet, multi-jet fusion, or like SLS material space. And a lot of them are using nylons and have all these like particles kind of loose floating around. A little bit different from what we have, but there are now some physical chemical vapor processes that can smooth out even nylon materials. So those are kind of fun things that we can you can check out our website for, or you can happy to talk a little bit more about it here.
Another set of questions that have also come through have been along other materials available on the printers. We hear you on that one. We're, whether that's PLA, PETG, ABS, there's a lot of interest in those materials, and sort of the way we approach it here at Markforged is we're always open to ideas, and in the background always experimenting with a lot, as some of you might be doing yourself. But for us, the big thing is understanding what the market needs are, as well as pairing it up with ensuring that the quality of printing any of these new materials holds up to the standard we have for our Onyx materials. So that's kind of where I'd leave it at. And like personally myself would love it if we could print many more things. I know Charles would as well, if we could get it to print the same way we have our current materials.
Yeah, I've seen this implemented a number of ways. Like so far, you get one color as long as it's black, right?
Yeah.
For Markforged, it's Onyx or it's Onyx or it's another Onyx. I at home I have some like hobbyist grade printers that I use for like quick prototypes and PLA and PETG. So I hear you on the PETG, that cost. I get it.
Yeah.
I think relative to depending on what the thing is that I'm printing, like if it's just for myself, then yeah, I think I want to manage costs. But in a lot of cases, I'd say I've had a couple of prints fail, like even though I'm pretty meticulous about my bed leveling, like sometimes you just get a part pop off, or I've had like out of material stuff too. And it's, yeah, we hear you on the other materials. That's all I'm going to say.
Yeah. That's where we'll leave it at. We have a bunch of other questions, so we'll get to those in a bit. We'll dig into some customer stories using fiber here, just to give you an idea of the range of applications. Some of you may be using them in similar ways, so we can go ahead and proceed with that there.
Cool. And we do have like almost like a full lesson, right? So see about, we can either blitz through these or we can save the other ones for the next time. Let's see how this goes.
Yeah.
Cool.
So first here on the list, we have Humanetics, which works in the space of like making crash test dummies and doing collision tests of that sort. And they developed a thermoset mold, which was for a neck ring that went on one of the pieces of these mannequins. And so here's one of those cases where the fiber of choice was high strength, high temperature fiberglass because of those higher heat elevation properties for heat deflection. Here we have 200 degrees C for 36 hours was the application temperature. And so this is one of those things where the Onyx material alone would not have sufficed for both the clamping forces from the bolts as well as the temperature. But you get a whole new set of properties by implementing fiberglass. So this is one of those use cases where you have to anticipate what your conditions are going to be. And that ties back to that earlier question of workflow, right? You start off with understanding your requirements. And so here, Humanetics understood that they were going to be operating at these, slightly higher end limits of the material. So they try to figure out how to make that combo, which is the beauty of composite materials, is that you're able to leverage multiple properties across the board.
Yeah, so in this case, I think this 200C is actually above our stated heat deflection temperature. Which heat deflection is very like a specific test, right? You get a beam and you're putting a point load in the center. I think it's flexural beam that you're putting a point load on, and then you're like slowly elevating the temperature until eventually that beam like compressed, like it flexes to some amount. So the mold, I think for the most part, although there are these small clamping forces, I'd say the biggest thing that this mold would be subject to is actually just like gradual warp. So just slumping or creep, if you will, like kind of heat creep, that where it's just kind of slowly creeping. What the HSHT does in this case, it has the same. I think of our fiber reinforcement materials, it does have the highest heat deflection temperature.
Correct.
So it's on the same order of like it's in the same range as onyx, whereas the other fibers are at like the 110, 110 C range. This is 150 C. So it's not like at 150 C, it's like suddenly deflects. Right?
Yeah,
It's
that's not going to lose all its properties all at once at one limit.
Yeah.
And this is a proof that you can go above and beyond that. I mean, depends on also the geometry, how thick this part is, how much fiber you're packing in.
Yeah, cool. Another example. What's this guy?
We have a machining soft jaw. So this, as you can see, has some dowel pins put in place for sliding and locking this piece that is being machined. Here, the application required or ended up using fiberglass. Fiberglass is sort of the workhorse of the fibers, right?
Yeah.
Would you just find it as that?
Like for me personally, I'm out here saying that Onyx Pro is the best value machine out there. I love the fiberglass because it's an all-rounder material that's it's like pretty good in compression. It's pretty good in flex. It's like pretty good in tensile, and it's half the price of the other fibers.
Yeah.
So it's a good place to start. And like, rather than saying like, let me fill this part up with carbon fiber and kind of just go for it, I like to use concentric rings of fiberglass. I've got one machine set up at home that has it's just fiber. It's essentially an Onyx Pro. It's a Mark II, but like I only use Onyx fiberglass on it because it's quick and it's low cost. It allows you to print 100 microns still, and like if that's not enough, if you need it to be stiffer, you can always switch from fiberglass to carbon fiber. If this part is under like heavy impact loads and is just like eventually it's just like breaking, you can use Kevlar because that's going to keep it from tearing. Like Kevlar it doesn't like shear like that.
Yeah.
And then high temperature, you can use HSHT. So fiberglass, great all around material. And in the case of machining soft jaws, there are a lot of different ways that you could do this implementation. We've here shown the soft jaw that is kind of clamping two kind of strangely shaped sides. I would say that in some cases you may want to machine one side, right? You can have the conformal side, like the difficult side. Don't machine that, right? You can print that, and then have your the side where you put your datum maybe on the simpler side, right? So on the left side down here, you could probably that seems like a pretty easy pocket to mill out. So rather than doing this whole like kind of complicated pocket to hold your part, you could mill this side and just cut the time in half, right? So it's kind of up to you. Obviously, in this instance where you print both, you can just print it overnight and not worry about it.
Yeah. The other thing there as well is just being able to leverage the fact that Iger gives you print times as soon as you upload a design in there. So as soon as you upload that design and maybe the time is longer than you expected versus what your machinist might be able to do, then you might say, hey, I'm going to just send over this part to my machinist instead of printing it, because you instantly know what that time is going to look like, as well as the cost.
Cool. Inspection fixtures. Been trying to get my dad to do this.
Oh, really? What's your dad do?
My dad is, so our family business is in, I'm obviously not working.
Yeah.
I'm just like talking about them. We do manufacturing of pistons,
okay,
and a variety of cast machine components. So yeah, like this obviously not as high stakes as turbine blades, right? JJ Churchill makes turbine blades, and our stuff is like on the order of like 1 micron accuracy, right? Like their stuff needs to be much finer than that.
Yeah, and that's where carbon fiber comes in, because carbon fiber is super stiff. It is often used for these precision applications where you need that rigidity in your inspection fixtures. and need minimal warp and deflection over time, especially if you're coming in and clamping down that fixture and then coming in with your probe as well. You want everything to be as accurate as possible, which means it doesn't move. And that's where carbon fiber comes in and kicks butt. And then here's another example of that where you also need that rigidity. Brooks Automation, working here in, looks like semiconductor wafers. So you need something that's stiff as well and high precision. You know, those are the keywords that you'll kind of see again with carbon fiber applications, is stiff and high precision. You're able to avoid any warp in your part, both while printing and afterwards, which is honestly the more critical thing. As Charles mentioned, with our test, you want your material to sort of be in an ambient state after a certain amount of time. You want it conditioned. You don't want it immediately tested after you print it, because that doesn't really represent how your part will be used.
Yeah. And in this case, actually, I went and visited Brooks probably about 2 years ago. They used this not only for like some certain small volume stuff. I think this one in particular was used for actually as a prototype for an aluminum part, because they're going to make these in higher volumes, right? They're making like a semiconductor manufacturing line. So they wanted to test out functional designs before they ended up going in. But if you were to print this in another material, like just onyx, for example, wouldn't necessarily be stiff enough to do this. So carbon fiber for sure lets you get close to those properties that you want for metal parts, and then do your functional testing, iterate the design, change some features up, and then you can go into a machine component. Oh yeah, Valkyrie here. So BattleBots is, if any of you here have seen it or are fans, is we call it a very high impact sport. They've got these robots that are just essentially destroying each other. And one of our former content engineers, Alex Crease, was a competitor. I think he still is a competitor in BattleBots. So Team Valkyrie had this skid pad that they used on the bottom of the robot, and this allowed it to essentially absorb a lot of impact. And despite that, it was also spinning very quickly. So they needed this thing to spin and not like tear apart. I think in some cases, with some parts, like with impact and with high speed, Kevlar really is kind of the best material to hold it all together.
Mm-hmm.
So it's a bends but doesn't break is what Kevlar is all about.
Yeah. Another example here. We're gonna just briefly update this, just adjust some changes to the slides here. Okay, there we go. Other example here, Kevlar, again, this is on a prosthetic device of sorts to help for stroke mobility. You want some of that deflection, and you have dynamic loading here in this use case. So again, another great application for having that strength and resistance, but you have a little bit of give with Kevlar. And additionally, on top of that, it's relatively light compared to anything else that you might try to produce this device out of. But now that'll bring us to workflow and principles for fiber applications, which is where I want to dig in a little bit into how to think about your use of fiber. So this is sort of the way we like to work on using fiber at a high level. Come in, identify your functional requirements and load conditions. That will entail identifying where your loads are at, the range of force on them, as well as then using that to figure out if you even need fiber. And that brings you to the second step, where it's like, if you do need fiber, what fiber type are you going to use? You know, those customer stories are examples of areas in which you have to identify what fiber you're going to use. Like fiberglass would not have been enough for that high temp application. The next big thing is part orientation. Part orientation drives everything, or quite a lot, with your part. The way your fiber is going to be routed, surface finish, you know, your Z strength. And then on top of that, the last thing you need to do when using fiber is figuring out how to lay your fiber out. And at the end of that, you're going to circle around through this cycle of printing, testing out, and iterating, figuring out if the way you set up your part was enough to meet those initial requirements. So what type of load conditions exist? You know, there's kind of a range here, but the common ones are, you know, tension, bending, torsional forces, compression, and sort of point loads on different surfaces within your part. And you can kind of see those here. You have just classic cantilever beam type forces. You have compression forces coming in. Here, the example is a tube bending die. You have forces coming in from the machine keys that are producing torsions within the part. You have compressive forces from bolts. These are just a couple of examples. But knowing that, the big question then becomes, how do I set up my part? And so the big thing with trying to set up a part is to leverage the fiber properties. And the guiding concept here is continuous fiber is strongest in tension. So whatever you can do to orient your part so that fiber is in tension, that is essentially the way to go. You want to optimize for having the most amount of fiber put within tension, given the loads that you're experiencing. And despite your part, maybe experiencing compressive loads, that doesn't mean that your fiber isn't going to be able to feel tension, because what you feel at a macro level on your part is different from what the fibers are going to experience. So you can imagine sort of a point load coming on the exterior wall of this part. Although that would be a compressive force, it is locally putting those fibers within tension, which is why you'd want to have like concentric rings.
This was like really counterintuitive to me at first.
Yeah.
Because really any sort of load that you place onto a part can be in a lot of ways translated to another load. And when we make the load bearing material, this like concentric reinforcement fiber, like really it's like anything really bending, even torsion in some cases is putting tension on the material. So it is really about leveraging your design skills to adjust your design such that everything is in as much tension as possible. And it's a lot, it's actually easier than you might think.
Yeah.
Yeah.
And so we'll dig into some of those concepts in a bit. So when to use fiber, how to use it. So here's some data that we built out on the concept using beam deflection. So we ran a couple of internal tests on our own just to pursue these curiosities. This was done by someone that was here a while back. And more recently, I took that data to just make some comparisons about, what does it mean to add fiber in this orientation or add extra sandwich panels. And so with beam deflection, the big thing is sandwich panel theory, which some of you may have heard of, where if you put fiber on the extreme ends, you're able to increase the strength of the part proportional to that gap size.
Even with just like a regular non-fiber reinforced parts, you're seeing kind of similar theory. Like when you print an onyx only part, there's material on the very outer surface. And I think if you were to say add more infill versus add more
roof and floor
layers, you'd get different properties. Like if you wanted compressive properties, I like for the part, like overall kind of in the Z direction, I would add more infill because that the more dense, more material you have there, the more weight it can bear.
You have the cell structure helping out there.
And but if you're in bending, you want to put all the material really on the outside, right? So we're saying that the materials are kind of highest, the materials are loaded the most on the outer surfaces. So you really want to put more material where it's going to be put into tension. So that's kind of what you're seeing in this beam bending example.
Correct. And so here are some of these examples that I mentioned. So this is an example where we printed these 10 millimeter thick tabs, and we made a comparison of going from 0 carbon fiber layers to 8 carbon fiber layers, 4 on the top and bottom. And so here, the big things to highlight are the change in price, as well as a change in the flex modulus that you have for this part. So this is one of those examples where for 2.7 times a price change, you're able to get over 7 times the amount of flex modulus on this part. So this goes back to the sandwich panel theory. So here you get, a large amount of benefits from adding fiber to not having fiber if your loading condition calls for it. The next example is what happens if you already have fiber and you want to add a little bit more fiber, going from 4 layers on the top and bottom to 8 layers on the top and bottom. And from here, you can see that you only get 1.3 increase in your flex modulus, but you're going up about 1.6 times the amount in cost. So you're not really reaping as many benefits as in the previous case where you had no fiber and experienced up to almost 7 times an increase in the modulus. So these are things to consider as you trade off the cost and benefit of adding fiber.
Oh, just a quick clarification here. The percentage change, that is like that's not like 1.5.
Yeah, sorry.
That is like the ratio change.
Yeah, so that would be 132% change there. Good call. And then other examples, as Charles mentioned earlier with the compressive forces, what happens if you change the infill of the part? Here, we're not even adding fiber, which is the more expensive part. Here, we're just adding more onyx. So we went from having triangular infill between these sandwich panels to doing solid infill. And so you can see that the price increase is very little, but you're able to go about 1.6 times the magnitude in the modulus. And so, you know, for very little price difference, you're able to get a stronger part just by adding more onyx material. So these are the big ways to sort of think about what strength you're really reaping out of these parts.
This one's interesting. So I think this beam and bending, it's not really like the fibers that are failing when you bend it. It's actually the infill buckling.
Yeah, the infill collapses internally. And so by making that solid, you're able to sort of address that concern, which is why you see that modulus increase there. But just a quick wrap up here on these techniques. I know some questions have come around, you know, how to best route fiber, how to help out parts to make them strong. So one of the examples is for addressing issues of bending, as we saw. So sandwich paneling, you're going to want to do an isotropic fill on the top and bottom layers. And you can see this on this drone arm, which is experiencing that load there. A question came in about how to address torsion. So a quick way to address torsion is to take this isotropic sandwich panel design and add a bit more fiber by adding stripe pattern of isotropic layers in between. That helps address bending with the sandwich panel, but then by having these alternating fiber layers in between, that helps address some of that torsion with your more traditional fiber layup pattern, going from 0, 45, 90, 135 angled fibers in between, because you're putting those pieces in tension when they twist. So you can see that being addressed there. And the final tip here is if you ever have any point loads or compressive forces against the walls, adding concentric rings around those walls is the best way to go about that. That addresses anything coming in from the side. If you did have a force on top, then having isotropic patterns would be great for, you know, resisting any deformation there, because those fibers will, again, as mentioned earlier, be put locally in tension, counterintuitively to the idea of it being compressed. And so with that, we wrap up today's presentation and want to be able to get to your questions, which we know there are plenty of. We hope you enjoyed what you saw, and hopefully we can dig in a bit to any more of the specifics as we go through the chat.
Feel free to throw in suggestions for the next customer webinar as well. Like, we want to make sure that this is useful for you, and you know, it's all well and good for me to come up here and wax poetic about carbon fiber, but this has to be useful for you. Otherwise, it's not worth me doing. Addressing the torsion question, actually, I wanted to do a quick answer on that.
Yeah.
I actually ran into this as well, where I actually had essentially a robot gripper, like a very long, thin robot gripper that needed to enter a space and was loaded. So it was like an arm like this, but it was loaded down here. So it ended up causing this kind of this torsional load. The best resistance to torsion as far as composites go is, I think it's a tube, right?
Yeah.
Is to have a tube. So the reason why the tube works best, like, I think tube, because especially if it's tube per unit of mass, because you're concentrating all of the material as far away from the center of the moment arm as possible. So in resisting torsion, I think there are a few things that you can do. Some of them are more complicated than others. Design wise, if you have the space, if you have a decent amount of volume, that like clearance that you can have, I would say expand out the cross section of that part, right? And you can use a very sparse infill on the inside, but you can use continuous fibers on the outside. So that way you're getting more resistance against torsion. The isotropic fill also functions better when you have a larger width. So if you were to take a rectangular cross section, by blowing that out and having more isotropic panels, you'll actually get better resistance to torsion. You'll still want concentric on the outside to resist, like when you torque it, you want to resist the compression on the edges. So concentric on the outside, sandwich panel of isotropic through the center, but really the key parts are the isotropic top and bottom.
Yeah, correct. And one question that did come in here is, wouldn't the limitation in torsion be the layer adhesion versus the fiber strength orientation? Yeah, correct. It's double trouble there, if you will. And that can be addressed in two different ways. One is to, use external hardware to help with that compressive force to keep the part intact and avoid any delamination, whether that's adding, a nut and bolt situation. But on top of that, having overall macro level strength, it does how to have sort of those isotropic panels, because it really comes down to how much torsion you're experiencing and what those angle limits are. Because if you're never really reaching a point where you're hitting a high angle where those layers begin to peel off, then you want to be able to still have that strength within the part from the isotropic panels. So as a general rule of advice, would leverage both using isotropic stripe fiber as well as, including any hardware. Does not hurt to have that, because, it really comes down to which of those limits you end up hitting first.
Yeah, and I will say, like, in the end of this, like that example that I had, I think the best design that we came up with was actually to print the mounting point, and then to print the actual end effector. So like the very end of it where the load was being placed, and have the set, like that whole long center section be a rectangular tube. So we got a woven 45.
Okay.
Like, so essentially the 45-degree angle tube is like optimally made to resist torsion. So it ended up being a composite of composite parts.
Yeah.
And so I won't say that, by using fiber in this way that you'll make the best material possible. I think there are definitely shortcomings to this. As you said, the layer adhesion is a very big component of torsion. And if I were trying to break a really stiff beam like that, that were printed on a Markforged machine, I put it in torsion.
Yeah, definitely. And with that, like the big thing with torsion ends up being, at the 45-degree angle, that's where you're experiencing the max amount of like principal axis stress. So, and that's one of the great things with Eiger, is that you're able to specify sort of the angles of those fibers across the different layers. So if you have an idea of the way the torsion is going to be applied, then you're able to adjust that within the part design in Eiger. And that brings us to this other great question about how do you determine the amount of layers of continuous fiber? So this kind of goes twofold, and Charles might have his technique on this one. You can run back of the envelope calculations is one thing. You can pair that up with iterating and testing, which is possible because of being able to turn around parts relatively quickly while 3D printing. And on top of that, it circles back to that initial idea of being able to understand your different load conditions. I'll give you a story for an example on this. I was working on a end effector for a robotic welding arm, and we were trying to see what deflection would happen at the end of that arm. And so I ended up using the cross-sectional area of the fiber along with sort of its tensile modulus to figure out the individual amount of stress that a given fiber could use. And so I then kind of multiplied that out by how much fiber I needed to include in each layer. So that's like one big way to go. But I think the first thing is add fiber to the extremes of the part, like the sandwich panel, you're adding fibers top and bottom, and then working your way in throughout. And for testing purposes, start off with fiber at the extremes, test it out, narrow it in, add a bit more fiber if you realize that didn't meet, your criteria, and then go in from that. So start, from least amount of fiber up and see how that holds in there. And then figure out what orientation you should put that fiber in, because if you go and put concentric rings when you should have been using isotropic, then that's not going to really benefit your test case.
So I've gotten like this question has come to me two ways. One is, what is the optimal amount of fiber that you should put in a part? And then one, I think, which really it's like, how much should I put in, right? Like the question is, how much should I put in? But really what I'm hearing is, what's the minimum amount? So the way that I do minimum amount of fiber ballparking is to actually look at the volume fraction in the part. So if it's a part that's like relative, let's say like simple loading, if it's in bending or if it's in tension, you can use a volume fraction to figure out just how much you have. And there are a number of ways you can do that. If it's a simple cross-section part and like every layer is kind of the same, you can do just like do concentric rings and then path it And then you can do some back of the envelope math to find out, all right, how much volume of fiber do I have relative to the volume of that STL file, the whole part. And that will give you a great ratio. So let's say you wanted to print a very simple, let's say it's like a chain link, right? And you've got a chain link with a let's call it a square cross section of like 1 centimeter. And you want this to be half the strength of aluminum in tension. So you can take the number and tension for aluminum and then have that be like equal to essentially the strength of carbon fiber times the volume fraction plus the strength of onyx times the volume fraction.
Yeah.
And then that will give you an approximation on how much tension you want it to be. If you look into the design guide, actually, we have essentially kind of plotted out like, I'm not sure it's that clear in the design guide, which makes me think I need to make another tool for everyone. So if anybody's interested in like a fiber fraction calculation tool or like a fiber strength calculation tool, send a note in the chat and we can include you. And if you want to work through this tool, I think it's something that I've like kind of started working on, like have different versions of, but it's not very user friendly. Yeah. So maybe I can turn it into like a web tool.
Yeah. Another way on that one, on the technical side that I like to use is taking the materials property table and then doing sort of a rule of mixtures to find an upper bound and lower bound modulus for composites using like the Roos model and the Voigt model to kind of help out get an overall bulk modulus for your material. So if a table of that interests you as well, we can try to pursue what that would look like to give you at least upper bound and lower bound limits on combining fiber within these parts that you're working on. And quick question that I can answer here is there a minimum or recommended part thickness in order to use carbon fiber and other CFR materials? So usually the minimum part thickness I recommend is being able to have, what is it? So 4 and 4 sandwich panels of fiber, and then being able to have another 4 layers of floor and roof above and below that. So that would put you at approximately like 16 layers of thickness.
We have this exact answer in the Markforged composite design guide.
Right.
I'll do a quick screen share here as far as the or actually can we throw a link into the chat?
We can.
To
panelists
and attendees. Okay, here's a link to the Markforged composite design guide. I think this is the latest version. If you open that up and flip down to, I want to say it's like page 10, maybe. No, not this is expanded. This got really, this is good. Wow. It's page 5 actually. Page 5 will tell you what the open, like the small, like the minimum open loop feature is and the minimum so open feature versus looped feature. So an open feature means that you got the fiber needs to go out and back. And the looped feature is just kind of going around a loop. So what we've recommended there is 2.8 millimeters wide for the loop feature. I found that in some cases, like really tight bends, that you want to go like slightly bigger than that. And then for the open feature, 3.6. So kind of I think those are good numbers to work off of.
Yes. On top of that, if you haven't answered the poll, go ahead and answer some of those questions there. That'll give us some ideas for how to come back to you with useful information that can help you progress any of the projects that you're working on. It seems like digging into the lesser known Eiger features seems to be a popular thing of interest. So, maybe on our next webinar, we can just do an Eiger demo and work through a part and show you how we'd set a part up or multiple parts, especially on the fiber side.
Yeah, cool. Let's see. There were a lot of questions early on, I think, about HSHT? No.
We have questions on coating and water resistance with Onyx.
Oh, great questions. I I think that this is a thing that's very near and dear to me.
Yeah.
A question that has been bothering me since like the dawn of time that I've been here. So moisture is like definitely affects onyx, right? We were talking about it being a hydroscopic material that enjoys absorbing all the moisture out of the atmosphere and kind of equalizing. So that does two things. One, it actually increases the toughness of the material, believe it or not. So it makes it less stiff, but it also makes it more durable. So it can withstand more impact as it's been plasticized by the moisture. There are a number of coatings that I'm looking to try. So if you have ideas of coatings that you'd like to see attempted or experimented on, let me know. And I'll coordinate with our materials team to see if we can get some more testing done. The thing that I found, like as far as research goes, to be the most promising is actually a polyurethane coating. But so a polyurethane, like a spray coat even could be pretty good. If you were to prime the material with a plastic primer and then paint over it, I'm looking for the easiest solution.
Yeah.
And Cerakote sounds like I've heard that recommended. Liquitex, I think, is an acrylic varnish, which has also been recommended. Anything that really seals the surface and is not moisture permeable is going to be a good choice for that.
Do you know anything about, I know someone was asking about Cerakote?
Yeah, I have not done Cerakote, so I'll add that to the list, the short list. We should probably go through all of this list of questions here.
We're gonna go ahead and dig into these questions and hopefully pursue some projects out of some of these interesting questions that keep coming up, because there's a lot of interesting stuff that we'd love to investigate if we haven't already, or get answers to you if they are already there. Best place to go is definitely our website. We have a lot of great resources there, a lot of content. All the tech specs are on there for our materials, which seems to be, super important here for these applications, and being able to make sure you can use and leverage these materials properly.
And if we did not get to your question, we will. Are we gonna? Yeah, we can. There are not that many. We'll respond to you. We'll send you an email. But I think between the two of us, we can hash out these questions and get you an answer to your questions. As far as I saw a question about turbo infill. So like really on the infill, the number of infill questions. So turbo infill, I think, like theoretically should be about the same. I would say that we've seen better layer adhesion at
layer heights, or thinner
layer heights.
Yeah,
but interestingly enough, I think at the turbo print is okay because it's actually printing hotter. So I would say that the biggest issue with turbo print, as far as the turbo infill, specifically like doubling the layer height of the infill on the print, is that in some cases with a shallow curve, it may not give you the same resolution of infill going up the part. So you might see, like in some cases there may be gaps where regular infill would not leave. But if your part is mostly boxy, no like gradually sloping shallow surfaces, or has mostly like kind of like steeper surfaces, like just not past 45 really, I think you would be okay.
Yeah. But looks like we've come up on time. Like Charles said, we'll follow up on any of these questions. Maybe we might just send out a answer sheet with like top questions asked with answers to those, and we can compile that so everyone has access to them. But I think with that, we'd love to just thank everyone for joining us today. We hope you were able to pull something out of this that you can take back and implement with your printer, and look forward to chatting with everyone again in a future webinar.
Yeah, send Charlotte your feedback, Charlotte@markforged.com. I'm sure she's going to love this.
But no, appreciate everyone joining, and we hope everyone has a good rest of their day.
Cool. See you, everyone.
Thank you.
Thanks.